Welcome. So in this lesson, we're going to be talking about factorization of polynomials, which is exercise 6c. It says, since the aim of factorizing a cubic is usually to solve an equation or to find the x-axis intercepts of a graph, the first step is to establish whether a particular linear expression is a factor of the given cubic or not. It is possible to do this without actually doing the division process. Okay, so let's pause for a moment and kind of reflect upon what they're saying. So what we need to do, first of all, is determine whether or not the linear expression is a factor of the given cubic. So for this question right here, it says let p of x be equal to this cubic and divide p of x by x minus 2. So what we want to figure out is whether our linear expression here, so this is our linear expression x minus 2, we want to determine whether this is a factor of our cubic here. Now, the way in which you determine whether something is a factor of something else is you divide it and see whether or not you get a remainder. So what do I mean by that? Well, let's use a simple example. So you don't have to write this down, but let's just use a simple example to show you what I mean here. If I had 6 divided by 2, that's going to be equal to 3, and I don't get any remainders out. The remainder is 0. And because I get no remainders out, what that tells me is that 2 is a factor of 6. So because I was able to go 6 divided by 2 is 3 and get no remainder out, that tells me that 2 is a factor of 6. It goes in perfectly, and that's the definition of a factor. But alternatively, if I went 6 divided by 4, well, 6 divided by 4 is goes in once with a remainder of 2. Well, because I get a remainder of 2 out here, what that tells me is that 4 is not a factor of 6. 4 is not a factor of 6 because you got a remainder out. It didn't go in perfectly. So the way in which you determine whether something is a factor of another number is by dividing and seeing whether or not you get a remainder out. So let's use that exact same logic over here, and let's determine whether x minus 2 is a factor of p of x here. So let's give this a go. So I have x minus 2, and then I have, let's go, x cubed plus 3x squared plus 2x plus 1. So this is where I do polynomial long division, and this takes some time. So I'm going to go, this is x squared, x cubed minus 2x squared minus, this will be 5x squared, carry down the 2x. Then I start again. This is going to be 5x. This will be 5x cubed minus 10x, bracket, bracket, minus. This will be 12x, carry down the 1. This will be plus 12. Then I'm going to get 12x minus 24, bracket, bracket, minus. And I'm going to end up with 25. So that means I get a remainder of 25 out. So this right here is my remainder. And because I got a remainder of 25, what does that tell me? What does that tell me about my linear expression and my cubic? Well, what it tells me is that x minus 2 is not a factor of p of x because I got a remainder out. If I got a remainder of 0, that means it is a factor, but it didn't. Okay, so as you can see, it's kind of a bit of a long process, therefore, to determine whether or not something is a factor of something else, because you have to do polynomial long division. Well, this is where this last sentence comes into play. It says it is possible to do this without actually doing the division process. So we can determine whether or not something is a factor of something else without doing polynomial long division. And now we're going to learn how to do that. So over here it says now find p of 2. Now why exactly are we doing that? Well, we know that our linear expression is x minus 2. We're going to set that equal to 0 and then solve for x. And then what we're going to do after that is sub into p of x. So we're going to sub x equals 2 into p of x. So this is the process that we're going to do. And we know that the way that we write that is just saying p of 2, which means every time you see an x, you're going to put a 2 in that spot. So I'm going to get 2 cubed plus 3 2 squared plus 2 2 plus 1, which is going to be 8 plus 3, 2 squared is 4, plus 4, plus 1, 8, plus 12, plus 4, plus 1, 20, plus 5 is going to be 25. Well, would you look at that? Where does that look familiar from? This is our remainder. So by doing this process, by taking the divisor and setting it equal to 0 and solving it for x, and then subbing that into our polynomial, we have found the divisor. And therefore, we could immediately say that, you know, x minus 2 is not a factor of p of x. That's pretty amazing. That's far quicker and far simpler than doing polynomial long division. It's like a shortcut. Now, this actually has a theorem attached to it. This actually has a name for what we've just done. It's called the Remainder Theorem. So the example above suggests that when p of x is divided by x minus alpha, the remainder is equal to p of alpha. So take a note of what they're doing there. So x minus alpha would be this. When we set that equal to 0 and then solve, we get that. And now, if we go p of alpha, we know that this result right here is going to give me the remainder. That's what that line there is saying. So this is in fact true, and the result is called the Remainder Theorem. And then we have a nice little description of it here. The Remainder Theorem, when p of x is divided by this, so a linear expression, the remainder is going to be p of alpha over beta. So again, if I was just to show you what's happening here, let's just come over here. We've been given this as our linear expression, so beta x minus alpha is, when we set that equal to 0 and then solve, we would get this, and then we could find the remainder by subbing that into p of x, and this right here would give us what our remainder is. So exactly the same process over here, just a little bit more complicated because of this beta there. Perfect. And then you might be asking yourself, well, hopefully you're not, hopefully I've explained it well, that you're not asking yourself question, what is the point of the remainder theorem? The answer, we can find the remainder without actually performing polynomial long division. Now, let's just kind of go through a little proof here of it. So here we have the following. We have p of x is divided by x minus alpha, and our answer is going to be our quotient plus our remainder over the divisor. So the divisor is here, so remember the remainder goes over the divisor. Now it says multiply both sides by x minus alpha. So what that means is we're going to multiply this side by x minus alpha, and we're going to multiply this side by x minus alpha. And when we do that, well, what's going to happen? Let me get another color here. Let me get green. This would cancel with this. This would cancel with this. And I'm also going to, get times x minus alpha there, right? Because this is multiplying, if I was to do it this way, this is multiplying there and there. So that means what I would end up with is this right here, p of x, because now this is gone, is equal to q of x times x minus alpha, because this times that, plus r, because this went away. We get this. Now, what happens when we let x equal alpha? So if I was to let x equal alpha, what I would end up with is q of x. Now, I'm going to go times alpha minus alpha, because I'm letting that x be equal to alpha, then plus the remainder. I'm going to get q of x. Well, what's alpha minus alpha? It's just 0 plus my remainder. Anything times 0 just goes to 0, so it's going to be 0 plus my remainder. And that means I'm just left with my remainder. And that's kind of the proof of what we're doing here. When we have our divisor and we set it equal to 0 and then we solve for it and then we sub it in as we did here, let x be equal to alpha, you end up with just getting the remainder out. So that's kind of like a little proof of what we're doing there. Perfect. So that's kind of just an introduction to the remainder theorem. Hopefully it makes sense why we're doing all of this. In the next part, we'll go through some examples together. So I'll see you then.